let's perform machine learning on the MNIST dataset and see how well it can classify the different numbers. Now, to expedite this process, I want to go up to the top here, and we're going to change this. Instead of 20,000 rows, which will take a little bit too long, we're going to change the number of rows. And you can do that using in rows equals, and then let's try to put in 2,000. And similarly with the test set, say in rows equals, I don't know, maybe 200. Okay, so we're cutting down the number of rows to speed up just testing to see how it actually does. Okay, so what we're going to do, we're just going to runtime run all, rerun all the data so that it updates with the new df and df test with less rows. Okay, now recall as we're setting up our x and y, what we're trying to predict is going to be this 0th column, and x is going to be everything else. Okay, so let's go down to where we have a new coding cell, and we can say x equals, and it's df.iloc. So we want all the rows. We'll start with the first column and take every other column. Similarly for x test, we'll use the df test.iloc, and we'll take all the rows and the first column and all the rest. Now y is df.iloc, still in all the rows, but just the first column, and same with y test. We want to do the same thing on the df test set. So again, it's .iloc. It's always rows, comma, columns. Okay, so they're setting up our x and our y. Now let's start with logistic regression. Logistic regression is a classifier. It should go ahead and classify this. So, and I say should because, okay, so we're trying to predict like 10 different numbers, the digits 0 through 9. And logistic regression typically is used for 2, but it is built in as a straight classifier, and so it should work. So from sklearn.linear model, okay, we are going to import logistic regression, and then we can go ahead and initialize our model. Model equals logistic regression. You need the parentheses, and also this max iter so we don't get an error, so it doesn't converge. Set it to about 5,000. Next, we can fit it on the data, model.fit x comma y, and then we'll go ahead and score it on the training data, x test, y test. Okay, so let's see how logistic regression performs on the MNIST data set. Got an error. It says, oh, is it really that imbalanced? It says the solver needs samples of at least 2 classes in the data, but the data contains only 1 class of 0. That's surprising. Did I do this right? Let's check. Y, x comma y. It's possible. Oh, I see what it is. This is wrong. This should be 0. You know, I think it's the first column. We want the, it's the 0th index is how you get the first column. Okay, so rerun that. And now come down here, run this again. And we get 90%. So pretty good job, right? Like it's correctly classified 90% of the data. This is accuracy. So if it said this one was a 5, it got it correct. If it said it was a 2, it got it incorrect. Okay, let's see if xgboost can do better. All right, so what we're going to do, we're going to import xgboost. And from xgboost, we're going to import against a classifier, so the xgb classifier. Okay, then we go ahead and initialize the model. Model equals xgb classifier with the parentheses. And then, just like before, we'll go ahead and fit it on the training data, and we'll score it on the scoring data. Model.score x test, y test. That's our test data, right? And recall here that this is data that it hasn't seen during the training, and so it's looking at new ones. Okay, so we will go ahead and run this. Not sure what I see the red underline, it disappeared. Now xgboost, recall, it builds 100 decision trees for, you know, each like round, you could say. And so, it takes a little bit of time because it is in fact 100 models here. Whereas logistic regression, right, it's one machine learning model. It's got to find the convergence once. XGBoost has to find the convergence 100 times. So it is taking a little longer, but we should get a score relatively soon. And do note that we're not using any training here, but we do get a slightly better score at 91.5%. Now, is the model overfitting? It probably is, okay? We don't know that, but we could figure it out. We could try something like this. We could score it on just X and Y and see, okay, how does it score in the data that it was trained on? Does it get higher than that? Oh yeah, it gets perfect. So it perfectly classified all the data we gave it, so it's clearly overfitting. So what you can do, we could just copy this in. You could try some of the parameters that like call sample by level, just to give you an example. Call sample by level will cut down the dependency on certain columns. And so if we try 0.75, say, and then we do the same thing with call sample by node, just to put a couple in there. Okay, so this is my knowledge that what this will do here is it won't overfit on the columns. Each kind of round, you could say it'll be like 75, it'll only use 75% of the columns available to it. Could even go lower, I think. Okay, so just making a couple small changes just to see, will that in fact give us a better score of 91.5? Okay, and hopefully it will. However, we're going to see how deep learning is going to do. We're going to build a neural network on this. So what we're doing is we're looking at the MNIST dataset in terms of stages of different kinds of machine learning models to see how they actually perform. And you can see I did get the score up to 0.93 just from making those two changes. So that's pretty solid. And you might wonder, like, hey, how strong can we get with XGBoost? And feel free to give it a try. Try some grid searches or some random searches using cross-validation and see how high you can get that score. But what we're going to do next is we're going to see how neural nets perform.